of the very center of the Andromeda galaxy. Anne-Marie's already mentioned this. This is innermost few arc seconds of Andromeda taken from WIFPIC, and you see it's got a double nucleus. At the center, there's a bright spot and a faint spot, and there's also a small clump of bluish-looking stars at the fainter spot. This is what it looks like when you look at the old light, the reddish light, and you see it again becomes much more clear. Then if you place a slit along this double nucleus and you measure the kinematics of the stars there, you find that you get a very steep change in your velocity. You get very steep velocity gradient close to the center. You get a steep rise in the velocity dispersion at the center. And interestingly, the peak of this velocity dispersion is not coincident with the bright peak of the nucleus, double nucleus. Okay, so here's then some characteristic scales of this system. So this is a double nucleus. The luminosity is a few million times that of the sun. You've got two stellar peaks, both of which seem to have identical old red stellar populations. They're distinctive from the surrounding bulge, but essentially they're very old and red and boring. And there's a hint of there is a very definite young cluster of blue stars at this fainter peak. Right. And this fainter peak, of course, is the photometric center of the galaxy to better than 0.1 arc seconds. And the separation between the two peaks is about 2 parsecs. Right, 2 parsecs. Characteristic velocity rotation, the difference in velocity is about 200 kilometers a second. So when you put in the sums and you work out what the characteristic dynamical time of this is, it's about 10 to the 4 years. Right. And so that raises the question of how can you explain this? It's something that's presumably dynamically very old. If you were to imagine this as being two distinct clusters, well, first of all, you'd have to explain why do they have almost identical colors, and why wouldn't they have spiral into one another by dynamical friction? Right? And I think the only game in town for explaining this is Scott's eccentric disk phenomenon. So this starts from making the initial assumption that the potential here is purely Keplerian. Then you use the thing that you learned as an undergraduate, which is that all orbits in Kepler potentials, or all bound orbits, are ellipses, and these ellipses don't precess with time. So all stars in these characteristic elliptical orbits, the characteristics characterized by 2 numbers, the size and shape, and then 3 numbers that tell you what the orientation is. Right? And because stars linger at apocenter, you tend to find a bright spot off the black hole. Right? So this is a blob of stars with a blob of orbital elements and a fairly eccentric orbit, 0.7. This is what you see if you look at it from top down. Disk axis, I'm going to call this is going to be the x-axis, the long axis of the disk. The z-axis is the short axis that's coming out of the board. And then we're free to rotate this, to view this clump of orbits at any angle, any orientation, and that gives us 3 Euler angles to play with. So here's what it looks like. If you view it from the side, you see now you do get a peak close to the black hole, but if you invoke Goldilocks and you look at just the right angle, you see you get a very nice double nucleus. Yeah. Okay. So there we have with this snapshot of an eccentric disk. And what I want to do in this talk is to say, what can we learn just by looking at this snapshot and trying to model it? So that's perfect because it gives me an excuse to be as dynamically unsophisticated as I can. Right? So I'm not going to try to put in any knowledge about evolution of how this system should go according to Balescu-Lenard or anything like that. I'm just going to say, I believe in Newton's laws of motion. If I apply those to this, what can I learn? Yeah. Okay. So the simplest thing to do is essentially to stay with Scott's original simplifying assumption, which is that this is a purely Keplerian system. Right? And I think the best example of this is this paper with Pyrus and Tremaine in 2003, where they wrote down a phase-space distribution function for this disk. So essentially, it's a Gaussian in eccentricity a Gaussian in inclination, and then there's some modulation which says what the distribution of semi-major axes is. Yep. And by tuning with the forms of these distributions, the parameterized forms of this semi-major axis distribution, the eccentricity distribution, and the inclination, the puffing up, they were able to get pretty good fits to the observed kinematics. So here's an example here. This shows the velocity as a function of radius from the center, and you see it agrees pretty well, but there is this annoying offset here that fails to explain. This is a feature that basically is, as far as I know, is impossible to explain. Yeah. And they can also explain the peak in the velocity dispersion profile and puts it in the right place, roughly the right magnitude and so on. And an interesting fact about this is that if they allow the orientation of their disk to wander around freely, they get a better fit when their disk isn't aligned with the host bulge. Okay, so of course you can do it better than that. Well, with a lot more work, but you can do slightly better. So what I did with my graduate student, Callum Bryan, was to just generalize the Pearson-Tremaine distribution function slightly. So we didn't want to think too hard about exactly what semi-major axis distribution to take or anything. We thought let the computer decide what that should be. So we took the essential form of the Pearson-Tremaine distribution function. Essentially, it's a sum of Gaussians in semi-major axis, eccentricity, and inclination. And we just let them have arbitrary weights. Yeah. So the only assumption that we really put here was we assumed this disk has some form of it's got two symmetry planes. The inclination or the orientation of that with respect to us is freely varying. The black hole mass is a free parameter for the models. And of course, we also have 810 weights that we're allowed to vary between 0 and a big number. And then we can calculate the contribution each one of these blobs makes to the observed photometry and kinematics, and we can jiggle the weights around in order to maximize that fit, trying to improve that fit. And it's not surprising that with 800 more parameters, we can do a bit better than Pearson-Tremaine, but just slightly, right? So here's an example just to show off what you can do with this very simple model. This is a fit to the photometry. I think it's pretty clear which one's the data and which one's the model. Yep. Here's a fit to the kinematics. This is the V rotation curve of the cluster. You see, once again, we failed to match this funny dip. Of course, it's flipped compared to the last time. But and then also shows here how the kinematics vary if you change the assumed black hole mass. So you see that the black hole mass is constrained to be roughly 10 to the 8 solar masses, but there's quite a lot of slop within that. There's the velocity dispersion proof. No. People know it, but they're all wrong. Yeah. Sorry, I don't know it. Let me put it, yeah. And no one knows it. If they tell you, they're lying. Yeah, right. The people who aren't lying would say about 1 by 10 to the 8-ish, plus or minus a factor of 2-ish, right? There is, but yeah, but I don't believe that. I mean, I'm sure John believes it, but yeah. Within a factor, it's actually twice as big as this. Yeah. Okay, so, but I think I would argue it's roughly 10 to the 8-ish solar masses, but I think the problem with this is you see systematics are a big deal. Yeah. Okay, there's the fit to the velocity dispersion profile. Again, it's slightly better than Pearson-Tremaine, but not hugely better. So, and even better, the models make predictions. So we didn't use this in making the models, but Bacon et al. Took OASIS integral field unit observations of the velocity field across the face of the disk. This was the rotation velocity field plotted here as the contour, plotted as the colors. And then our model predictions for that are plotted as the contours. So it agrees roughly the right orientation. It all works kind of okay-ish. There's the velocity dispersion profile. Again, pretty good. And whenever you look at higher order moments and so on, they tend to agree as well. Okay, just one problem with this, and that is it's a bit too unsophisticated, right? So we've assumed here that the potential is purely Keplerian. With that, you get this black hole mass of around 10 to the 8 solar masses. But if you believe a plausible mass to light ratio for the disk, that means then that the disk mass must be around about 1/10 of the mass of the black hole. So this Kepler approximation is a good one, but it's just a 0th order one. Okay, and Scott in his 1995 paper, of course, had anticipated this, and he pointed out that there was some mechanism was needed to maintain the apsidal alignment of this disk because of the fact that the disk is massive, the potential is not purely Keplerian, and therefore the apsides are going to precess, and then this disk will become smeared out. And he suggested that a promising possibility, he made a few suggestions, but he said the most promising one is probably that the alignment is maintained by the self-gravity of the disk. Yeah. So let's just be a bit stronger than that. Let's chance our arms and say that the whole black hole plus disk system is stationary in some rotating frame. And the first question is, does such an equilibrium exist? And secondly, what's the pattern speed at which this frame rotates? And then finally, what can we learn about the distribution function of the disk in this funny rotating system? Okay, so at this point, we want to say goodbye to Mr. Kepler and hello to Mr. Schwarzschild. Well, Mr. Newton and many other people in between, but we're going to culminate in Mr. Schwarzschild. So there's a bit of a problem here, and that is, as soon as you add this potential, what happens is your orbits become a real mess. Well, don't call them a mess, that's not really a mess, but they precess very slowly. This takes a slightly eccentric orbit, you put it in a reasonably realistic disk potential, and it just turns out into the nice smeared out distribution function here. And it becomes even worse if we allow the pattern speed of this whole potential to rotate with time. Okay, so there's two ways of dealing with this, at least two ways. One way is to be a good celestial mechanic and to think in terms of osculating ellipses. Another way is to say, computer time is cheap, student time is cheap too. Let's take Schwarzschild's method, apply it to Schwarzschild's galaxy. And I'm really worried about talking about this in Princeton because I'm afraid there's going to be a trapdoor that's going to open if I say something wrong here. Okay, so then this is work that was done by my graduate student, Callum Bryan, who's just finished. So we've got a few more parameters in this now. So we've got the potential is the black hole plus the disk. Then we've got the parameter, one parameter to the black hole mass. We've got 3 parameters describing the orientation of the disk. We've got the stellar mass. We've got the pattern speed. And we also have the unknown 3-dimensional density distribution of the disk. Right. And so our procedure for modeling this is essentially just standard Schwarzschild. You take our best guess Kepler model, you take the density profile that it produces. You calculate the potential corresponding to that. Then you use Schroeder and Tuma's version of the method of averaging, generalized to generalize the potentials with a constant pattern speed to try to pick out centrophobic loop orbits. So we try to avoid lens orbits because we want something that's going to be long-lived. So we deliberately avoid any orbit that comes close to the black hole. Right? And we find this method works extremely well in the plane, but we couldn't successfully generalize it to selecting orbits that are out of the plane. That's just still an unsolved problem there for us. Then you fit these orbits to observations, and then an optional thing is you can go back and try and improve with an improved guess for your stellar mass distribution. So, as I said, this is painful to do well. It's just computationally very expensive. The main reason being that these orbits precess slowly. Okay, so Callum has done this. He's scanned over all kinds of parameters. Along here at the bottom is the inclination of the orientation of the disk. There's the black hole mass. You see 2 by 20 by 2 by 10 to the 8 is pretty strongly ruled out. There's the disk mass and there's the pattern speed. And what he finds is essentially that the main constraint on the disk mass actually comes from the ratio of the disk mass to the pattern speed. That's very strongly constrained there, but the disk mass itself isn't. Thank you. And you can even iterate this to self-consistency. So here's, you take your data, you make a guess for the potential, find the distribution function, find the stellar mass density, that gives you new potential, go back, keep repeating this. And then this is what happens to your density distribution as you do this. There is what we start off initially from our Kepler model, and then first iteration, fourth iteration. So it does seem to converge towards a self-consistent DF.
Is it your color table, or there are various color tables in this talk?
and they're not all consistent.
No, but I mean, the fact that it seems to have steps.
Yeah. No, sorry. Yes, that's a good point. Yeah. So the point. Yeah, thank you. I didn't ask you to ask this. Right. This here has got billions of points in it. These ones here only have about 1,000 orbits. Right, because it's so expensive to do this. So you can only follow for a small number of orbits. Okay. And there's, example of the fit. That's model, that's observation. We're not quite fitting noise, but we're getting close. Kinematics, wonderful. Except we really can't explain this funny dip here. And here's a summary of the thing. So the inclination there is 57 degrees. It's misaligned with the main body. The bit mass is 10 to the 8. Blah, blah, blah. The pattern speed is very slow. Okay. Right, more interestingly, I think, is what does the distribution function of this look like? Right. Here is what we get. That's what the initial Kepler models say. This is what the final iterated model says. And thankfully, it did come out clearly. So what you can see here in the black curve here is the eccentricity distribution, right? And just as was predicted in Tremaine 95, is that you do expect this negative gradient in this, right, in order to get the eccentric disk, right? That becomes a bit softened in the self-consistent model. It holds everywhere for us, except at the very center, where we find that the model really, really likes to have a negative eccentricity. So that means anti-aligned retrograde orbits. They're not plotted here. The other thing that I got really excited about when I saw this was that the ratio of the dispersion and eccentricity to dispersion and inclination is 2 to 1. And that also holds roughly in the self-consistent models. I was really, really excited because this made me think about the solar neighborhood, where we know the ratio of velocity dispersions in R to the ratio of velocity dispersion in Z is 2 to 1. And also from, say, if you look at two-body relaxation and axisymmetric disk, that's predicted to be 2 to 1. The only problem is it's the wrong way around. So what we find is the ratio of dispersion and inclination to that eccentricity is 2, whereas these more standard arguments say it should be a half. But we can explain that. Right. So I'm sure most of you immediately thought, yes, we can immediately explain that using resonant relaxation. Right? So here's an example of if you take a ring like this with various eccentricities and you use Gauss's method then to calculate the dispersion rate of inclination, eccentricity, inclination, and upsidal, you find that if your disk is eccentric enough, then you do expect this dispersion and inclination to be bigger than that in eccentricity. So it's just an example of vector resonant relaxation being faster than the scalar. Okay. So does it work? Kind of. So here's a simple n-body simulation I took. Here's the Hamiltonian for one of the stars in this system. You can split into 3 parts. You can split into, with respect to the black hole's frame, there's a Kepler part due to the black hole. There's an indirect term due to the fact that your frame of reference is moving, and then there's another bit due to the star-star interactions. Right. And last week, I wrote a quick multivariable symplectic integrator, so like essentially a solar system integrator, to try to integrate this system. Unfortunately, I chose a time step that was too small, and I chose a mesh spacing that was possibly a bit too coarse, so these haven't run for very long. But here then is going to be a movie. This is Callum's initial condition, or his best fit model. And ideally in this movie, it should be really, really, really boring. Nothing should happen, right? Something does happen, but it's, so nothing happens, nothing happens, nothing happens, nothing happens.
Is this a rotating frame?
This is an inertial frame. So it should just process, that's all. And it does process for a bit. And then it kind of loses the will to stay together. But on the other hand, there's a well-defined pattern. The pattern persists. So you see here it's becoming a bit decoherent. And then it thinks, let's get it together again.
How long is this?
This is, because of this stupid thing, this is about 3 days.
No, sorry, I mean.
That's I knew. This is the whole thing's 1 million years. Yeah. So only 1 million years, and precession time is just about 2 million years. So I get to about here and then I stop. Or I got to a few days ago. But it persists. Here it is in the inertial frame, just to prove to you that it really does work. So this is what Callum predicted in his models, 1.65 kilometers a second per parsec. That's what he found in the Schwarzschild model. I should say these are completely independent. Callum doesn't know I'm doing this. Well, he does now. But and you see it does stay with the pattern speed that he predicted. And okay, this also explains why it doesn't work. Right? If you look here, this is the edge-on view of the disk, and you see that it has these features which are due to our inability to get the vertical sampling done well. And that's, I think, the reason why, or the main reason why this isn't in a perfect equilibrium, because we haven't successfully solved that problem yet. Okay, so it's still working, it's still persisting, but I'll move on to conclude. So then, conclusions. So this, right, as we all know, the Scott's 1995 model provides the only viable explanation for these P1, P2 double nucleus in M31. The black hole mass in this system from these models is around about 10 to 8 times the mass of the sun. A new feature from Callum's work is that if you want to have a self-consistent black hole plus disk model, then you're required to have a low pattern speed. I think the limit Callum found was about 6 or 7 kilometers per second per parsec. And something I'm not going to mention unless somebody asks me is this provides a possible explanation for the young stars, P2, P3, that surround very close to the black hole. And by looking at the distribution function of our best fit model, we find this broadly consistent with what you expect from resonant relaxation, just the fact that the dispersions are not what you expect from two-body. Okay. So there's some technical shortcomings. First of all is the most obvious one. The model isn't in perfect equilibrium, and that's because the vertical sampling is difficult. And of course, it could also be just that my n-body integration isn't all that good. I mean, it hasn't been checked in great detail. I think a tougher problem to crack is that we don't really understand the errors in the data. So in the data that we were using, the bulge kinematics had been subtracted. We really like them not to be subtracted, so we could subtract them ourselves. So that's an issue in trying to understand the outer parts of the disk, right? And does it precess retrograde and so on. Okay, then there's some more interesting problems that I think you can move on to. First is that we've made this pretty strong assumption that the system is biaxially symmetric, so it's got two planes of reflection symmetry. But why should that be? I mean, perhaps it's warped. Perhaps it's maybe like a persistent warp going on. Once we have this n-body model, then you can start to think about stability. You can start to probe it in more detail. So maybe let it run for a bit, let it settle down. Then see if we can find things like Anne-Marie's pendula, or almost like a donkey effect in how the orbits behave. And another question we haven't addressed, apart from the fact of how did this form, is why is the disk misaligned with respect to the bulge? So we've put this in complete isolation. We've ignored the fact that it's embedded in a bulge, which seems to be triaxial. And what effect does that have? We haven't done that. Okay, so thank you.